Okay, class. So last video we were talking about the second fundamental theorem of calculus. In particular, the second example might have been a little bit mind-boggling for you, where I started using some of these variables, where this u came in. And so today I'm just going to end up doing some more stuff about the second fundamental theorem of calculus and just a couple of examples. So here we're going to be talking about the second fundamental theorem of calculus. And this is going to be part 2. Now, I'm going to just remind both of us what the second fundamental theorem of calculus is. And so, as we wrote down yesterday, and be sure to put this in your notes again, there's definitely some advantage behind repetition. So the derivative of the function of this entire thing, which is the integral from a to x, f of t, dt, is just going to be equal to f of x. Now the problems that we're going to be solving, we're going to be eventually getting to this format, but we're going to do it in a little bit of a roundabout way. And it might be a little bit easier for you guys to solve problems in this way. However, I want you to be comfortable at least seeing things like the variable of u and being able to use them in order to solve certain problems. Okay, so the first problem is going to be, say I've got a function f of x, capital F of x, and this is going to be equal to the integral from x to 8, or from 8 to x, sorry, of the cube root of t dot dt. Okay, and so in this problem there's two parts. One is I want you to find, or to integrate f, or to integrate this function so that we can find f. And we're going to demonstrate the second fundamental theorem of calculus by then taking the derivative of this function, right? So in this case, this would be our capital F of x. The derivative of capital F of x is just going to be equal to f of x, which is what our original function is, with the t replaced as an x. Okay, so our answer, so A, we're just integrating. Integrating to find capital F of x. Okay, and so when we do this, you guys don't be too worried about the t, don't be too worried about the x. It's pretty much straightforward, just if you consider the variables as numbers. So the first thing we need to do is to take the antiderivative. So we can say capital F of x is going to be equal to, and the antiderivative, actually, you know what, I'm going to take one more step, and I'm going to rewrite this from x to 8. And I'm going to say, instead of the cube root of t, I'm going to call it t to the 1/3 power, that dt. Okay, so now I can take the antiderivative pretty easily. So I can say t to the 1/3 plus 1 divided by 1/3 plus 1 from x to 8. And when I do this, I get t to the 4/3 divided by 4/3 from x to 8. Which is equal to, and I'm going to flip the bottom fraction so I can say, okay, this is going to be equal to 3/4. Instead of dividing by 4/3, you multiply by 3/4. 3/4 t to the 4/3 from x to 8. Now my f of b in this case is going to be f of x. Okay, so I can say my overall f of x is equal to, so in this case it's going to be 3/4, and I'm plugging my b value, which here is x, so now I've got x to the 4/3 minus, now I'm going to plug in 8 for t in this case, and so I'm going to say 3/4 times 8 to the 4/3. Now 8 to the 4/3, cube root of 8 is going to be 2, and then 2 to the 4th power is 16. So I can rewrite this and just say 3/4 x to the 4/3 minus, in this case, this is going to be 16. 3/4 16, which is just going to be equal to 3/4 x to the 4/3 minus, and then 3/4 of 16 is just going to be 12. So this is my f of x, my capital F of x. This is the first part of my problem, determining what that is. Now the second part of my problem is I want to integrate, or I want to differentiate this. So instead of capital F of x, I'm looking for f prime of x, which is also going to be equal to df dx, which brings me back up to our second fundamental theorem. So I'm taking the derivative of the function. Now this is going to be equal to, if I remember derivatives, this should be pretty easy, right? So the power rule says this 4/3 comes out front, and then I subtract 1. So I end up with 3/4 times the 4/3 out front, x, and then I subtract 1 from here, so I get x to the 1/3 minus, and then the derivative of the constant, as you know, is just going to be 0, so minus 0. Now the 3/4 and the 4/3, multiply those together, those just become 1. And so all I'm left with is just x to the 1/3 power. And sure enough, what I find is that f prime of x is equal to x to the 1/3, which is 100% equal to f of x, small f of x, which is going to be t to the 1/3 power right here. Okay, so I sort of just proved to myself that the second fundamental theorem of calculus holds. Now, the next example that I want to do is a little bit trickier, okay, and it's going to be more similar to the example that we left off yesterday with. Okay, so all you're tasked with here is finding f prime of x. Okay, and so f of x is equal to the integral from 2 to x squared of 1 over t cubed dot dt. And so once I recognize this, okay, so this is basically the problem that we just did. First I need to integrate this, and then I need to find the derivative and see what it looks like. Now there's two different ways to do this. I'm going to start, oops, I realized I just was totally off the screen. Sorry. Here's the problem. So I realized that there's two different ways to solve this. I'm going to start by doing it the long way, which is exactly the way that we just did the previous problem. And then I'm going to jump into sort of the shortcut way, which I want you guys to focus on and think about in terms of using it as a shortcut. So it's going to be involve using the variables that we did in the previous example, or not in the previous example, in the example from yesterday. So the first thing we need to do is focus on this antiderivative. So I'm going to rewrite the problem. Capital F of x is going to be equal to integral x squared to t, instead of 1 over t cubed, I'm going to say t to the minus 3 dt. So just bringing that t up, nothing to it. Now I can successfully do the antiderivative without too much effort. So it's going to be t to the minus 3 plus 1 divided by minus 3 plus 1, x squared to 2. And then when I keep going, right, so I simplify this a little bit more, minus 3 plus 1 is going to be t to the minus 2 divided by minus 2. This is going to be x squared to 2. And sure enough, when I start plugging this back in, just like I did previously, okay, I'm going to get, first let me do one more iteration of rewriting this. So I'm going to say 1 over minus 2, and then the t in this case flips down, so I get t squared in the denominator, and it's going to go from x squared to 2. So now I'm going to start plugging in these variables, or these values, the limits here. And so x squared is going to be the top one, so that's going to be my f of b. And so in this case, it's going to be 1 over minus 2 x squared, so just plugging that in for t, squared, minus, in this case I need to plug in my other limit, which in this case is 2. So I go 2 to the 2 squared. So if I rewrite this, so here I've got a negative negative that becomes a plus. So I end up with 1 over minus 2, and then x squared squared is x to the 4th, because squared to the squared, of course, you multiply the two exponents. So I get negative 2x to the 4th plus, and I get 2 squared. Here that's going to be 4. 4 times 2 is going to be 8, plus 1 over 8. So here's my answer. This is what f of x is equal to. f of x is equal to 1 over negative 2x to the fourth plus 1 over 8. Now, if you remember, I'm looking for f prime of x. This is most of the way, but it's not quite there. So now I can just quickly do the derivative here. So rewriting it, I'm going to say f of x is going to be equal to negative 1/2 x to the minus 4 plus 1 over 8. And then so then I can say f prime of x, the 1/8 goes away, the negative 4 comes out front, so I say negative 1/2 times negative 4 x, and then this is, instead of negative 4, this is going to be x to the negative 3, or sorry, negative 5, goes the other way, so I'm subtracting 1 from there. And then the plus 1/8 goes to just 0, plus 1/8. And so this just becomes negative 4 times that. This is just going to be 2x to the minus 5th. Awesome. So that's going to be my f prime of x. That's the total answer. So that's the first way to solve this. Okay, so a little bit more straightforward, might be a little bit more obvious. Okay, so first I take the antiderivative, I plug in the values, and then I can take the derivative of the function. Now, the second way I want you guys to be able to solve this is using the second fundamental theorem of calculus, and just like the example that we ended yesterday's video with. So starting over, okay, I realize that f of x is equal to, and this is just exactly what we started with, x squared from 2 to x squared of t to the minus 3 dt. Now, if you remember what we did, okay, so I said this thing right here, this x squared, is kind of freaking me out. So I can say, all right, u is going to be equal to x squared. And then I can rewrite this as from 2 to u of t to the minus 3 dt. And so then I can actually do this derivative and start seeing, or not do this derivative, do the integral and start seeing what happens. So I take the integral, or, sorry, I'm getting a little bit ahead of me, getting a little bit ahead of myself. So this is going to be f of x. So I know I'm looking for f prime of x, and this is going to be equal to df dx, or if I want to use that chain rule now that I've got it in terms of u, I can just say this is going to be df du times du dx. Now I know what df du is, so this is going to be my fundamental theorem. So I'm going to replace df du with ddu of this thing right here, of this integral of u to 2 of t to the minus 3 dt. And now I still got this du dx out over here, du dx. Okay, so here I've got, this is exactly what my fundamental theorem is saying, okay? So all I need to do at this point is just take this u, plug it in there, and I'm good to go, at least with this part. So that's exactly what I'm going to do. I'm going to say this whole thing, I'm going to get rid of the t's, plug in a u, and basically just say this is going to be equal to u to the minus 3. Now this du dx, I'm going to sidebar over here, so I know what u is equal to. U is equal to x squared. So du dx is going to be equal to u prime, which is going to be equal to 2x. So when I get down here, and I look at u to the minus 3, I can say, okay, this is just going to be equal to times 2x, which is du dx right there. Now if I remember, u is equal to x cubed. Okay, so now all I need to do is just substitute. So I've got x cubed, or x squared, sorry, u is equal to x squared. X squared to the minus 3, which is what I was saying, cubed, times 2x. This is going to be equal to x to the minus 6, so 2 times negative 3 is going to be negative 6, times 2x. I've got an x to the first power here, and an x to the minus 6 power. I can combine those two, and they're just going to be equal to 2, I'm going to leave the constant out front, x to the minus 5th power. And if I look at it, holy cow, this is exactly what I got from this longer way up here. So if you can understand this, if you can crunch your brain a little bit longer and figure out exactly what these problems are doing and how to solve them, particularly with the u's and the du's and the df du, this chain rule component right here, you can solve more complicated problems a whole lot quicker in less paper space if you understand them at a deeper level. Okay, so I'm going to leave you guys there. We're going to work on some of these harder problems in class tomorrow. I'll see you guys then.